So hi everyone, I am Jacinta. I work at the Bureau of Meteorology, and for reasons I'll touch on in this talk, this has contributed to my love of chaos theory. I'm not going to go into any maths in this talk, sorry for that, but I am going to cover quite a lot of reasons why software engineers should care about chaos theory. So we all build systems that we hope will be predictable, and this talk is why predictability fails and how we can design solid systems anyway. This talk was inspired by Lily's talk about falsehoods programmers believe about reality at PyCon AU. Specifically this falsehood. The more data we have, the more perfectly we can represent reality. If by the more perfectly we can represent reality, we mean we can predict what will happen next, that's very much not true. In this talk, I'm going to explain to you why, to discuss how chaos causes unpredictability in software systems, and to give you some strategies to handle it when it matters. But first, an example of how having all of the data doesn't give us future predictions. Consider briefly a lava lamp. You can know everything you need to know about it before you turn it on. How much water it contains, how much wax, what kind of wax, the properties of that wax under heat, what the heat gradient in the room is, what the temperature is being applied, the conductive properties of the casing, etc. And yet, once you turn it on, the convective movement of the wax within the lava lamp is random. You'll never see the exact same sequence twice. In fact, it's so random that SGI designed and invented LavaRand as a hardware random number generator in 1996. This is an idea still in use by Cloudflare in their wall of entropy. Having all of the data isn't enough to predict the future. Now, before I start, it'll be helpful if you're familiar with these words. So deterministic, the system always returns the same results for the same inputs. Dynamically unstable, small changes in inputs can cause wildly different results. An attractor, the stable state a system settles into. An integrable system, a deterministic non-chaotic system. Some people call them regular or stable. A chaotic system, a deterministic system that exhibits chaotic behavior. And stochastic, our randomness. So imagine for a moment a universe without surprises. A universe where every gust of wind, every heartbeat, every flicker of thought in your mind is no more than the inevitable consequence of everything that came before. A universe so orderly, so exquisitely mechanical, that if you could just measure everything, every atom, every force, every motion, you could predict the future with perfect accuracy. This has been a compelling idea for millennia. Cicero imagined that if you knew all the causes, you would know all futures, that time simply unwinds what is already there. If there could be any mortal who could observe with his mind the interconnection of all causes, nothing indeed would escape him. For he who knows the causes of all things that are to be necessarily knows all things that are going to be. For things which are going to be do not come out into existence suddenly, but with the passage of time is like the unwinding of a rope, producing nothing new, but unfolding what was there at first. Nearly 2,000 years later, Pierre-Simon Laplace published articulation of this idea, causal determination, on a scientific basis in his philosophical essay on probabilities. Laplace imagined a being that could look at the universe in a single, all-encompassing glance, a being that knew the exact state of every particle at every moment. And with that knowledge, it could compute the entire future, not just tomorrow's weather, but the rise and fall of empires, the orbit of every planet, the moment you would inhale your next breath. To Laplace, unpredictability was just ignorance. If you couldn't predict something, it was because you weren't smart enough, or you didn't have enough data, or your instruments weren't precise enough. But the universe itself, the universe was a clock, and clocks don't improvise. Then Poincare asked the universe a very simple question. What happens when we add just one more body? Newton's laws can perfectly predict the motion of two gravitational bodies, say the Earth and the Sun, but add a third body, even something tiny, and the equations explode in complexity. The three-body problem asks, given three masses interacting through gravity, can we predict their motion for all time? And for centuries, mathematicians assumed the answer was yes, if we were clever enough. And Poincare proved them wrong. In the late 1800s, he studied the three-body problem deeply. He developed new mathematical tools to understand it, and what he found was shocking. The system is deterministic, but dynamically unstable. Very tiny differences explode. Long-term prediction becomes unrealistic, and we had our first glance into chaos. Fast forward 7 decades. In 1961, Edward Lorentz, an MIT meteorologist, develops a computer weather model. It's amazing for its time. He decides to rerun the model again with what he thinks are the same inputs, carefully copied from a printout. He expects to get the same prediction. He gets a different world. The new simulation veers off course, slowly at first, and then violently until it bears no resemblance to the original. Lorentz thinks the machine is broken, but it isn't. The universe is. The printed values had 3 decimal places, and the computer's internals had 6. Rounding a decimal rewrote the future. What Lorentz discovered is that even in a perfectly deterministic system, tiny differences in initial conditions can explode into wildly different outcomes. A rounding error, a difference of 1 part in 1,000, was enough to rewrite the future. And with that, the clockwork universe cracked. Laplace's demon fell silent, and the butterfly effect was born. A butterfly flaps its wings in Brazil, and a tornado forms in Texas, they say. A decimal is rounded, and the weather system transforms. A packet arrives a millisecond late, and your distributed system collapses into chaos. We don't live in Laplace's universe, we live in Lorentz's. This quote is from Lorentz. When the present predicts the future, but the approximate present does not approximately determine the future. Lorentz's rounding error is the perfect parable for modern software engineering. In distributed systems, microseconds of timing drift can yield different outcomes. In performance, tiny perturbations can result in tail latency storms. In machine learning, minute training differences yield different learned boundaries. In numerics, floating point rounding yields diverging simulations. A chaotic system where these is one where these tiny minuscule differences have oversized consequences. Laplace's demon is a cautionary tale, because we can easily fall into the trap of believing that more data means more certainty, that deterministic code means deterministic outcomes, that simulations can model reality. But in complex systems, especially distributed ones, small differences in timing become big futures. None of the previous ones were true. None of these things do mean the other. And yet, there is shape inside chaos. When Lorentz plotted the long-term behavior of this simple weather model, just 3 differential equations describing convection, he expected a blob or a spiral or maybe a stable loop. He didn't just find sensitivity, he found a shape, a ghost hiding in the chaos, a butterfly the system can't escape. The trajectories of his model, no matter where they began, always fell into the same swirling, folded, butterfly-shaped figure. Not a point, not a cycle, something in between, a strange attractor. And this is why it's called the butterfly effect. So what is an attractor? An attractor is the state that a system settles into. If you put a marble in a bowl, the marble will eventually end at the lowest point. So that's a point attractor. If you push a pendulum, it will swing into a steady motion. That's a periodic attractor. If something spins through states, you often get a torus. Attractors feel like destiny, and Laplace would have been happy. But Lorentz shows us that destiny is complicated. Now, the twist, strange attractors. Strange attractors never repeat. They never settle. They're infinitely detailed. They live in fractal dimensions, not a line, not a surface. They have deterministic rules and unpredictable long-term behavior. And yet the system stays within the attractor, constrained chaos. Lorentz's model could wander, twist, fold, and diverge wildly. but it was always staying on that butterfly winged structure, always within the attractor, always bounded by the invisible mathematical rails. The system is free, but never that free. And what could we take from that? Chaotic systems have patterns, not just predictable trajectories. You can't get long-term predictions, but you can get statistics. And deterministic systems can look irregular, because that's normal in chaos. And yet, here's the critical distinction. Chaos is not randomness. Chaos is deterministic unpredictability, where randomness is non-deterministic unpredictability. Chaos has structure, strange attractors. Randomness only has statistics. In short term, chaos can be predictable, even when the long term it diverges. We even weaponize this deterministic but dynamically unstable functions to get pseudo-random numbers. The same rules with a different seed give us wildly different sequences. It's chaos harnessed on purpose, clockwork generating surprise. Once you see the structure inside in predictability, you can design for it. But first, let's go back to that lava lamp. The lamp is random because it's a chaotic system. Its behavior is highly sensitive to tiny, unmeasurable variations in its environment. It obeys the deterministic laws of physics, but the system is so complex that its exact long-term patterns are impossible to predict in practice. Even the most minute differences in the initial conditions, such as the exact composition of the wax, the thickness of the glass, the ambient room temperature, or air currents, are massively amplified over time, resulting in completely different flow patterns every time the lamp is run. Environmental factors like light changes, shadows, and physical disturbances also influence the wax's movement, adding further unpredictability. But chaos isn't lawlessness. It's rules that amplify tiny differences. Like a leaf in a stream, it has complicated motion but consistent eddies. You can't predict the exact future, but you can understand the shape. When you understand the system's attractors, you can design for resilience. Chaos is the universe whispering, there is order here, but you're going to have to work to see it. And this is where software engineering enters the story. Your systems have attractors, not necessarily mathematical ones, but behavioral ones. They could look like these. Under load, the system drifts into familiar failure patterns. Latency amplification loops don't appear by accident. Teams and code bases orbit recurring behaviors. Strange attractors show up as weird, hard to produce states that systems revisit just often enough that you know they exist, but not often enough to debug on demand. We call them edge cases or unknown unknowns, and chaos calls them attractors. It feels arbitrary, but it isn't. Every one of your systems are orbiting a strange attractor in the state space of that system. Their structure is just complex and sensitive and very high dimensional, very hard to see. But let's have a look at where we'll see this chaos to understand what I mean. Chaos appears in a bunch of places. Noise and scheduling and garbage collection pauses and microbursts and contention cascades and unexpected delays. These all cause unaccounted for differences from expectation. Each unaccounted difference is small, but together we get tail spikes where the average looks fine but the extremes hold the truth. Or probe storms, thrashing, feedback loops or retry loops, cascading failures and uncontrolled oscillation. We keep meeting the same failure shapes because we keep building the same loops. Lorentz showed us that even in chaos, systems don't wander arbitrarily. They orbit attractors, and the system can't help but fall into those, no matter how wildly it moves from moment to moment. And once you start looking at modern distributed systems through that lens, you realize we are building strange attractors all the time. We just call them something else. We call them incident patterns, tail latencies, the system being weird again. But that's structure, not geometric, behavioral. Design choices generate the rails the system rides. When we talk about resilience, we usually talk about making a system survive the unexpected. But chaos theory offers a different framing. Resilience patterns are engineered attractors. Circuit breakers push the system towards a degraded but stable state rather than a cascading failure. Bulkheads isolate one domain so that failure collapses inward instead of outward. Rate limiters pull the system back into bounded load instead of a runaway saturation. These are the attractors you choose. Without them, the system will find its own attractors, usually bad ones. A thundering herd is an attractor. A retry storm is an attractor. A consensus raft stuck just shy of quorum is an attractor. The question isn't whether your system has attractors. Of course it does. The question is whether you get to pick them. Have you ever debugged a distributed system where the logs tell you nothing, the metrics are flat, the traces look fine, but the system insists on drifting back into some slightly wrong state? That's a strange attractor. It's not random, it's not a one-off, it's a stable region of behavior your system keeps sliding into, of feedback loops you haven't seen yet. In debugging this kind of problem, the trick isn't looking for a single root cause. The core debugging question simply becomes, what invisible loop is pushing the system back here? In chaos theory, you don't find causes by looking forward from events. You find them by mapping the shape of the attractor the system keeps spiraling into. Observability gives you the tools, chaos theory gives you the mindset. Stop looking for the fault, start looking for the structure. A strange attractor is invisible in the equations. You see it by tracking trajectories over time. Observability is how we trace those paths. Metrics for axes, tracing for paths, logging for texture, high cardinality data for resolution. Together they reveal the shape our system inhabits under real load. And once the shape emerges, patterns stop feeling mysterious. And when you look, you will see those patterns. Maybe every retry storm starts with two services drifting 20 milliseconds apart. Every slow deployment path includes those same 3 nodes again. Every mysterious latency spike shares an identical fan-out shape. You're not just watching events, you're discovering the attractor your system lives in. You can't predict the moment a failure will occur, but you can predict the region in which it will be pulled towards, and you can design for that. This geometry exists beyond code. It shows up in teams. Misunderstandings between SRE and products. This always happens after handover. Everyone thinks it's bad, but why would we change it? These are human strange attractors, stable behavioral loops shaped by incentives, communications, patterns, and history. Chaos theory doesn't just describe computers, it describes complex systems, like teams, businesses, crowds. Chaos is everywhere. It's no coincidence that Lorentz encountered chaos when trying to predict the weather. Predicting the weather is hard. Consider a tropical cyclone. A storm is a vast, churning heat engine that is also dynamically unstable. A tiny wobble in the eye wall, a pocket of dry air, a slight shift in upper level winds, any of these can push the future hundreds of thousands of kilometers in a new direction. A single forecast can't capture that. It's one guess in a universe of possibilities. So meteorologists use ensembles. Instead of one simulation, we run many, each starting with slightly different initial conditions, a nudge in temperature, a tweak in pressure. Nothing dramatic, just the kinds of uncertainties that always exist in the atmosphere, magnified to reveal how sensitive the storm really is. The physics is deterministic every single time, but the outcomes are not. You'll see this in our forecasts. Individually, a tropical cyclone looks like, the potential paths of a tropical cyclone look like spaghetti, tangled, diverging, and chaotic. But together they form a picture. You start to see where the tracks cluster and where they fan out. Those clusters show regions of stability, and the fan shows instability, places where tiny differences explode into wildly different futures. Each ensemble predicts a single track, and together they map the shape of uncertainty, the geometry of what the storm could become. The mean of the ensembles, in black, shows us where to focus. This is chaos at work, deterministic rules generating a cloud of possible outcomes, all orbiting around a few preferred paths. In unstable systems, prediction isn't a point, it's a probability field. Ensembles embrace that rather than denying it. And in doing so, they give us something more honest. Not certainty, but understanding. Consensus algorithms live on the same edge between order and chaos. Paxos or Raft, whichever variant you prefer, all live on that razor edge. Consensus aims for a stable attractor, one leader, one consistent log, one agreed truth. It doesn't always work out that way. Under load, repartitioning, network jitter, the algorithm may fall into strange attractors. Timeouts align, votes split, leaders collapse and re-emerge. Watch the loop the cluster falls into when stress appears. The algorithm may begin orbiting a strange attractor. Nodes repeatedly time out at roughly the same moments. Candidates split the vote into the same occurring patterns. A leader is elected, collapses, re-emerges, collapses again, and the cluster drifts towards its metastable loop, just shy of that quorum. It's mathematically deterministic, practically unpredictable, structurally constrained. That means it's a strange attractor, although it's probably not a butterfly. Consensus systems don't fail randomly. They fail along paths. They fall into loops. They revisit the same difficult states again and again, not because of bugs, but because those loops are baked into the geometry of the algorithm itself. The system isn't just the code, it's the network, it's the clocks, it's the jitter, it's the chaos. One packet arrives 3 milliseconds late. Another server restarts mid-election. A timeout fires just a tiny bit too early, and suddenly the system forks, stalls, or elects a different leader. This isn't randomness, this is chaos. Deterministic rules colliding with unpredictable outcomes. But we don't eliminate chaos, we design around it. Distributed consensus lives in that shadow of Lorentz's butterfly. A tiny perturbation, a delayed heartbeat, a misaligned timeout can ripple through the system and change the outcome. And we make it work. We design the system so the attractor we fall into is a stable and safe one. We use randomized timeouts to avoid synchronized collisions. We use quorums to dampen any single node's impact. We replicate our logs and we converge on a stable attractor. We use failure detection to continuously correct and realign. Consensus is not a triumph of precision. It is a triumph of resilience. It's not Laplace's demon calculating the future. It's Lorentz's butterfly, tamed so that it flies in formation. So next time your system elects a leader, remember, it didn't do it because the algorithm is perfect. It did it because the algorithm is chaos aware. So I'm going to give some practical examples. OpenSSL, as you all know, is the open source library that keeps web traffic private. In 2012, a heartbeat was added, a ping where the other side echoes back your message to prove that it's still alive. The implementation had a bug. It did not check that the amount of data that you sent it to echo back was the amount of data that you received. And so anyone in the internet could send a one byte heartbeat that claimed to be 64 bytes, and the server would immediately echo back 64 kilobytes, pulled straight from its memory. That leaked whatever happened to be in that memory. Credentials, cookies, even private TLS keys. It wasn't a crash. It wasn't random. It was a deterministic code amplifying a tiny input difference, that payload length, into huge consequences. And that's exactly how chaos behaves, structurally constrained by a deterministic bug. Or another incident. On a summer morning in 2012, Knight Capital, a major US equity firm, turned on new code to support a New York Stock Exchange program. 8 servers were updated, and 1 was not. That single box still carried a repurposed function from years before. When trading opened, the unpatched box's behavior diverged from the others and began spewing orders. In 45 minutes, it sent millions of orders tied to just a couple of hundred customer requests, unintentionally accumulating positions that Knight had to dump the same day, locking in a $440 million loss. The cascade wasn't mystical. Deterministic code, uneven rollout, feedback from live markets created a runaway loop. One server's tiny difference amplified into a market-scale tail event. A single node broken symmetry, causing an attractor of propagation. Now those might just sound like bugs, but configuration choices can cause chaos as well. Imagine a service running imagine a Kubernetes cluster on a busy weekday afternoon. Traffic is high but manageable. Now, in Kubernetes, each pod has 3 health checks configured. A startup probe that gives the app a few minutes to boot, a readiness probe that says, I'm ready to take traffic, and a liveness probe that says, I'm alive, and if I ever stop responding, please restart me. Nice and easy. Now, introduce a tiny perturbation, something common and boring. A cache fills a little faster than usual. The garbage collector pauses a little longer than average. A downstream database hiccups for a second. Latency just enough that the app's readiness endpoint takes a beat to respond. The readiness probe times out. In Kubernetes, that means remove this pod from the load balancer until it says it's ready again. That's not a crash. It's a protective mode designed to keep bad traffic away while the pod recovers. When that pod is marked not ready, the remaining pods receive a slightly higher share of traffic. Tail latency grows for them too. Another pod's readiness fails, and then another. What was a single wobble becomes a broader shift, and traffic concentrates onto fewer healthier endpoints, which makes those endpoints busier, which makes them more likely to wobble. You can feel the feedback loop forming. This isn't hypothetical. Kubernetes documentation explicitly cautions that misconfigured liveness readiness probes can trigger cascading failures under load. Meanwhile, a liveness probe, perhaps, starts to fail on one of the struggling pods. Liveness is different than readiness. When readiness simply removes the pod from the traffic pool, liveness tells Kubernetes to restart that container. That restart takes more capacity away and increases more load across the rest of the system. As the container comes back up, the readiness probe hasn't started yet. It's still warming, so the traffic isn't routed to it. The healthy pods keep working harder. If the probes are tuned too aggressively, short timeouts, frequent checks, low failure thresholds, the cluster can tip into a repeating pattern. Readiness fails, liveness restarts, capacity drops, load rises elsewhere, more probe failures, more restarts. Engineers see this as a sudden flapping of traffic and pod restarts. And under the hood is a feedback loop created by deterministic rules interacting with small timing differences. From the outside, this incident looks chaotic. Dashboards show pods going in and out of service. Autoscalers may try to help by adding more replicas. Logs show readiness failed, liveness failed, container restarted. And the team is tempted to hunt for a single root cause. A bad commit, a noisy neighbor, a slow disk. The system is orbiting a strange attractor defined by its health check settings, back-end response characteristics, and current traffic levels. Kubernetes' own documentation emphasized that startup probes exist specifically to prevent liveness from killing slow-starting apps, and that readiness should be tuned to avoid needless flapping under transient conditions. Ignoring those guardrails is how probe storms begin. And how do you get out of it? The fixes are almost embarrassingly simple when you see the loop. You give the app room to start. You soften readiness. You lengthen your probe timeouts. You raise your failure thresholds. You want to dampen flapping rather than amplify it. You make sure that your auto-scaling and your probe policies don't fight each other. And then you observe it to make sure that your numbers are correct. And that's the heart of the story. Kubernetes probes are powerful tools meant to keep the systems healthy. But under certain timings, they can accidentally create an unstable feedback loop. The behavior feels random if you only look at individual events. It becomes legible once you look at the structure of the loop and tune the probes to break it. We can map our attractors. I'm going to give some ideas how. Unfortunately, I don't have time to go into a worked example. So first of all, make sure you're measuring the right things. Make sure your latency percentiles and stalls and long waits are counted, and ensure that your P99 and your P999 are real. Watch when the far end of your performance percentiles start amplifying. In probe storms, median latency looks fine, while your P99 is screaming. Your team popularized the idea of coordinated emission. Make sure you understand it. When your load generator quietly stops sending work while the system stalls, the biggest delays vanish from your stats. If your load generator hides long stalls, a classic coordinated emission problem, you'll only know that when it is a big problem. Talks and write-ups on latency measurement hammer this point again and again because teams repeatedly miss it during incidents. So mapping a chaotic attractor involves treating the storm's dynamics as a time series data set. So collect your probe success and failure counts, your latency, your CPU measurement, etc. And then take that data and map it into there's a conversion instruction here. I'm going to skip that bit, but convert your time series into a multi-dimensional representation. So you have probe success over time intersecting with probe failure counts, intersecting with latency, etc. There are tools to help you plot this, your reconstructed vectors in 3D. And then, in order to be sure that you can see the detail and separate out the noise, you can take slices, typically point cast slices, through your attractor to reveal those more intricate details. In the field of chaos engineering, the final step to understanding the attractor in your system is to inject failures into your system to make sure that it can cope. You can do this on a regular schedule, or you can do this while the system is wobbling, but not yet failing. You should consider doing this while the system is wobbling, so that you can validate resilience when your system is under pressure. So, for example, if the API latency is high, you can inject CPU stress and see if your autoscaling and retries really protect users. It can help you reveal weak spots in remediation. Chaos can uncover cascading failures that single remediation steps can't. Test your guardrails in production-like conditions. Build confidence that your automation will rescue you. And if your boss complains, you say, I'm not breaking the system. I'm making sure that my system has the desired attractor. There are actually a bunch of open source tools to help observe the low levels of your system. I haven't used any of these, but I did do a lot of reading of them and they look very cool. You can also use other open source tools to inject chaos into your systems. Add jitter, push your CPU, add stresses to your system. Because these are the things you can do, as I said, when your system's wobbly, not when it's failing, when your system is wobbly, just to make sure that it does recover the way you want it to. But maybe you don't do Kubernetes. Maybe you're a developer. So here's a story of a different chaotic event. Your team runs a fast API service. It's got Nginx, and most endpoints use async handlers. Upstream is a billing gateway. The dashboard says the average latency is 40 milliseconds. Life is good. Inside the code base, a handful of endpoints still calls upstreams using synchronous libraries, requests.get, because they were quick to write and they worked fine. Everyone assumes that the event loop and concurrency will hide any delays. It'll be fine. And then one day, your DNS provider serving the billing gateway hiccups. Queries that usually resolve in 2 to 4 milliseconds now take 120 to 180 milliseconds. just for a little while. It's not a failure, it's just a wobble. And then a request hits one of those synchronous endpoints. The handler performs request.get, which blocks the thread until the TCP handshake and DNS resolution complete. While that thread is blocked, the event loop isn't advancing, even though they're async. A few concurrent requests begin to queue. The garbage collector happens to kick in. Its short pause lands during the same window. You don't see much on the median, but on the P99, a cluster of requests jumps to 1.8 to 3.2 seconds, and customers notice. Your auto retry logic fires on the requests with fixed back off. Those retries increase concurrency just as the loop is starved. A couple more handlers use your synchronous clients and block as well. Now the queue grows and the tail stretches further. The service still looks fast on the average, and the dashboard's mean hides the amplification. Over the next 3 minutes, you see several bursts of P999 of 7 to 9 seconds. From the outside, it looks random. Weird spikes, then fine. Under the hood, it's a deterministic loop created by small timing differences. Sync IO in an async path blocks an event loop. Queued requests trigger retries, raising concurrency and queuing time. A garbage collection pause lands at a bad moment and adds a few dozen milliseconds. This retry, queue, stall, retry loop looks like an attractor for tail latency. Nothing here is stochastic. The code, DNS, garbage collection all follow rules, but the system is dynamically unstable. Tiny timing differences, a DNS hiccup, a short garbage collection setting, produce wildly different outcomes at the tails. You're seeing chaos, not randomness. Structure that you can't predict exactly, but you can't escape until you break the loop. Performance chaos isn't random. It's structure revealed in these tails. So we don't eliminate chaos, we design around it. We use load shedding and circuit breakers. We monitor percentiles rather than the averages. And we run these chaos experiments to expose our hidden fragility. Performance engineering isn't about making things fast. It's about making things predictably fast, even when the butterflies are flying. So next time you see chaos in action, don't ask, what went wrong? Ask, what tiny thing did I ignore that became a storm? Because in performance systems, chaos isn't the exception, it's the default. So we began with Laplace's demon, the dream of perfect prediction. Poincare cracked it, Lorentz shattered it, and our system mirrors the same behavior. And yet, we make these systems work. Not by pretending that chaos doesn't exist, not by trying to be Laplace's demon, but by embracing the lessons of chaos theory. We use ensembles in weather prediction because one model run is never enough. We use redundancy in quorums because no single perspective covers the whole distributed state. We design for tails, not averages, because chaos hides in the extremes. We build feedback loops and correction mechanisms because prediction alone is never enough. We measure honestly, observe deeply, perturb safely, and engineer the attractor we want. Chaos doesn't mean surrender, it means designing for a world where small things matter. Predictability is not the goal. Stability is. In complex systems, the limits of predictability are structural. Sensitivity, feedback, and high dimensionality reduce the scope of what we can predict. Determinism does not guarantee predictability. Predictability is not a prerequisite for reliability. Chaos isn't the enemy, it's just the environment. Our job as engineers is not to eliminate chaos, that's impossible. Our job is to build systems that stay stable despite it. Systems that bend, but don't break. If you walk away with one idea, let it be this. The future is not perfectly predictable, but it is shapeable. And understanding chaos is how we shape it. We can't make the future predictable, but we can make it reliably bounded. In Lorentz's universe, reliability comes from design, not prophecy. Thank you.
Thank you, Jacinta. Now, we've got a couple of minutes. Are you happy to take some questions?
Absolutely.
Okay, does anyone have any questions? Well, there we go.
This was the best talk I have seen in a decade.
Oh,
Awesome question.
Thanks so much. Thanks so much for the talk. Yes, very great analogy. But I just am confused a little bit from the comparison. Sometimes seems that you say the Laplacian demon does not agree with chaos theory. But as a physicist, I would say agree perfectly. The only thing is, if the demon also know the initial conditions, he can also predict the future, because chaos is deterministic theory, as you also mentioned. What Laplacian demons would not agree is with the random theories from like quantum physics. Can you give like a comment in that? Why do you think chaos and Laplacian demons do not agree?
If indeed we could model the entire universe, we could probably predict the weather for more than like 7 days. But the reality is we can't. Like we cannot gather enough information. We could put a weather station in every cubic meter of the entire globe, and we would still not have enough information because we couldn't account for solar flares. I mean, we would not be just by those observations. I agree that all of these things follow the rules, but the reality is the finer pieces of the information are just never going to be available to us. You know, a stream bubbles over a rock, a little bit of water gets splashed up into the air, suddenly that little bit of air is cooler than, you know, it might have been otherwise. If Laplace's demon literally could predict all of that, I still don't think it would be able to predict us. Like, I don't think all of my thoughts followed just from what they had before. Otherwise, dreams would probably be much less interesting.
You alluded to a method to convert like an event, a series of events from a log into a visualization of the attractor.
Yes.
How can I learn this magic?
That is an excellent question. What I would recommend doing is doing something like do a web search for visualize Kubernetes probe storm attractor, for example, something like that. The changing of the single time series, so latency over time, into a multi-dimensional, all of these observations over time, and then graphing them. There are a bunch of tools to do that. Obviously, there'll be a bit of noise because there's always going to be a bit of noise, and unfortunately, it can really matter that like the time series might not be accurate enough down to the millisecond. But there are some very good papers on how to do it, and once you've got your multi-dimensional thing that you over time, which you can then map onto your graph, as I said, there's it's called point pair slices. Allows you to try to make it, because it's not going to be 3D. It's kind of going to be more dimensions than that. So you can then take slices and have a look at what the slices are. There's some really good articles about it. If you can't find that from searching, find me later in the week and I'll see if I can find some more papers for you.
So you're going to be around all week?
I'll be around, yep, until Saturday.
Fantastic. Jacinta, I think you have managed to blow our collective minds. So thank you very much. Here's a little gift on behalf of the team, specially made for our speakers.
Thank you.
So thank you, Jacinta.